the fourth video, we're going to discuss the difference between a real gas and an ideal gas. So, first we're going to talk about what is an ideal gas. So an ideal gas is which the gases are point masses. A point mass means that it has mass but no volume. Okay. Second principle of an ideal gas is that ideal gases have random motion. In other words, the gas particles do not attract each other. Okay? And the third principle of the ideal gas is perfect elastic collisions. In other words, that when gas particles collide, energy and momentum is conserved. Or you could say energy is not lost as heat when the particles collide. Normally when two things hit, there's friction. Right? When your hands hit each other, there's friction, and any energy is transferred or transferred from kinetic energy into thermal energy. Okay? So a real gas is basically the opposite of these things. Okay, so let me start with point number 1 with a real gas. A real gas has mass and volume. A real gas, the motion is not random, meaning that the particles attract each other. And third, the collisions are not elastic. We would say non-elastic collisions. Now, the equation for the ideal gas formula is PV equals nRT. You remember that. Whereas the equation for a real gas is V minus NB times P plus A N over V squared equal to nRT. Okay? So, since the N over V is squared, the other way you can kind of write this is just A over N squared over V squared. Okay? So P minus NB plus, okay? B is the size of the gas molecule, and A is the attractive force of the gas molecule. Okay? So I'm going to go through this point by point and kind of explain what the heck is going on here. So for point 1, for an ideal gas, here's a real gas. So if I have a piston, and an ideal gas means that the gases essentially points with no volume. In reality, we know that gases are not points with no volume, but rather gas particles take up space. So, for an ideal gas, if we compressed the piston, we could push the piston all the way down until the volume equaled 0. In other words, you can compress the gas into no volume. But that is not the case. If you try to compress a gas, it'll turn into a liquid, and eventually that liquid will turn into a solid because the gas particles take up space, and eventually you will not be able to compress that gas anymore. So you cannot compress the volume down into 0. Okay? So an ideal gas, you could compress down to 0 volume. A real gas, you can't compress it down into 0 volume. So, how would I figure out this volume? Well, I could just measure it, right? But how do I figure out this volume? Well, the gas particles take up space. So I'd have to count up how many gas particles there were. And in my picture, I've got 1, 2, 3, 4, 5, 6, 7, 8 gas particles. And then I would multiply it by the volume of those gas particles, whatever they are. So the shaded area in red would actually be the volume of the container minus the number of gas particles times their size. Okay? So that's how you would calculate the red area for a real gas. Okay? And again, some gases are really big, some gases are really small. Okay? Now, maybe I don't want, I'll wait till the end. So principle number 2 and 3 are related, and that there are no attractive forces in an ideal gas. So, in a real gas container, in an ideal gas container, I'm going to make it bigger for us to see. In the fourth video, we're going to discuss the difference between a real gas and the rest in a real forces in an ideal gas. So, in a real gas container, in an ideal gas container, I'm going to make it bigger for us to see. And 8 gas particles, and then I would multiply it by the volume of those gas containers, the number of gas particles times their size. It's a real gas. And again, some gases are really small. So, and that there are no attractive forces in an ideal gas. So in a real gas container, in an ideal gas container, I'm going to make it bigger for us to see.